Hey everyone, welcome back to my channel where I talk about all things tech and finance. And in this video, we're going to be going over a very popular Ensemble method, which is bagging. What is Ensemble learning? Well, Ensemble learning is combining multiple models trained on the same data to get better results. This is used when we have a lot of relatively weak models that are poor at predicting on its own, but they are powerful when combined together, and when combined, we obtain a more accurate and a more robust model. Ensemble learning is popular with tree-based algorithms such as random forests, XG boosting, ADA boosting, etc. With all ensemble learning techniques, we want to optimize the bias variance trade-off. In other words, we want to have a low bias and low variance as you see at this point. Notice that the optimal point is not usually situated where the bias and variance intersect, since we still have to take the error into consideration. This is how you can visualize the variance and bias. Often, we can potentially decrease bias by having a well-balanced dataset and address edge cases and underrepresented categories. We can decrease variance by decreasing the degrees of freedom. You can think of the degrees of freedom as the number of features within the given model. Less complex models have less features, and less features are always better than redundant features for a given model. We know that using a typical single decision tree as a base model by itself is not going to be a robust model, as seen in my previous videos. A single decision tree can go one of two ways. One being that the tree has a huge amount of bias since the tree's height and number of child nodes are not enough in size, thereby only addressing a small portion of the data set. And two, being that the tree has too much information, as in categories within the tree are too wide, and thereby introducing a lot of variance. This is where we create an ensemble method where we can address both of these weak points, low variance and low bias, by combining a bunch of models together, thereby achieving a strong, robust model once we have everything combined. There are three algorithms to choose to pick which trees should be a part of the overall model, but we are only going to focus on bagging. Bagging is a form of ensemble learning which is known for bootstrap aggregating. This reduces variance and avoids overfitting a model. Essentially, this calculates the average weight parameters of all the trees considered, therein creating a model that addresses different scenarios. More often than not, in the real world, we actually don't have enough data to train a model that would be robust with independent, succinct data. Therefore, that is where bootstrapping comes into play. Bootstrapping is a sampling method that is really quite simple. The method assures that the data sampled is independent by sampling the data with replacements. This is also known as bootstrapping. And averaging the output for regression or majority rules for classification. We average these predictions to obtain a model with lower variance. A huge advantage with ensemble methods is that everything can be parallelized, and there are a ton of packages out there that do this for you. Now let us go to the demo and do this from scratch. So in this demo, I'm going to be doing somewhat of a hacky version of a random forest where I am going to be using many different trees and then just combine everything together to get an aggregate in order to get the bagging idea hammered home. And I'm going to be sort of doing this from scratch where I'll just be utilizing individual packages where random forest is actually very popular, but I'll just be doing this from like ground up and then sort of hammer home the sense of how to utilize bagging overall. So the library R part, that is essentially the regression tree package for like singular regression trees, metrics, parallel for each. So these two packages are related to just parallelize everything. So in terms of a multi-threading purpose, and I'm just going to be loading a few metrics in so I don't have to write my own. I'm going to be utilizing a nice data set, Iris, as always. It's always great for classification type algorithms, and it's like super useful. So I got 150 observations here and 5 variables over here. And then I'm just going to do like a real quick head of the data in case you're not familiar with it. We have different lengths and widths of a flower, and we are trying to predict the species related to the given data points that we are given here. And we have like 3 different unique values. We have Virginica, versicolor, and setosis. All right, so let's get our features. Just end features for number of features that we have over here. It should be 4. It is 4 actually. Yeah, it's definitely 4. And we just do call names of our data, and we are going to be calling 1 to 4 over here. This is our features. So we are taking out the species. That is what our target variable is going to be. So let's put in target and then call names data at 5 over here. Run that. And since we're going to be doing an aggregate method, we want to specify the number of trees. I'll just make this default at 100 over here. So we're going to be combining 100 different models together, and we are going to get an output. Or this would just actually just be features over here, and this would just be number of features over here, and that would just be 4 since we have 4 columns. Yeah, 4 columns, and these are just the names of the features. Yeah, there we go. Alright, so let us set up the parallel process of utilizing cores on our machine. This is related to CPUs, just to multi-thread our process. Call the number of cores, detect cores, really nice value here. We don't want to do any logical cores. We could just stick with physical cores. And space here. So we have, how many cores do I have? I have 8. So since I don't want to crash everything, I'm just going to let my cluster just utilize 7 of these cores. Let's run that, and then we want to register our cluster. CL. There we go. Okay, so let us actually create and implement our overall model. Call this models over here. We are going to be utilizing a parallel for loop that is going to look something like this, where we have 1 to number of trees, since we want to have 100 simultaneous models that are going to go through. So we can have 1 to 100 trees at the same exact time. We are going to be utilizing a few packages. Let's do parallel over here, and then randomly bag our features, And what I mean by bag, we're going to be retrieving specific values from our overall data set, and we are randomly going to be choosing of those features, let's say like 3 of those features every time. So let's do bagged features, and we're going to be sampling features over here, where features is our this is going to be our column names. We're going to be sampling 3 of those. So let's do size. Let's go 3, and we do not want to replace them. So we're just going to put that as false. Once we have our bagged features, we will then want to begin the bootstrapping technique, where we just randomly sample with replacement, so that we can have a large enough data set to calculate our overall model. Let's do like a random, what should I call it, like random index, or random sample index over here. And then we are just going to be sampling from our data sets. So that'll just be n number of rows of our data, which is the iris data sets. And we do want to replace it because it's going to be a bootstrap. So that's going to be a random sample index. So we'll be randomly retrieving random rows from our data set. Once we have our random sample index, we are going to be creating in the bag samples. And this is just going to be data of our random sample index. That's going to be all the rows. And then we have out of bag samples. Same thing, except we just take the negation of our random sample index. Okay, so once we have our training and testing data sets, we also want to create the parameters for our recursive tree. And there's a really neat function for this. It's just rpart.control. And this comes with default parameters, but we're just going to call this like tree control. And this is related to our hypertuning parameters, which is, it has all these as default. It determines where it's going to split the tree. The buckets via complexity parameters determines whether or not it wants to actually split based on that value, etc. So we're just going to stick with the defaults. We have a max depth of the tree as 30. So we'll stick to the defaults over here, but we're going to be passing all of these values into our overall tree algorithm. So let's call this just one tree. And then within this tree, we can call the R parts, and then it'll be formula is equal to as dot formula. Let's call this species, and this. So that should be our formula of that given data set. And then we want to pass in our data, which is going to be the ensample in the bag samples. And we are going to have our controls with the tree control over here. So utilizing the our randomly chosen features of our data set, we are going to be calling all of those features on that data set. But this data set might have like three of those different features that we have going on here. So it could be a sepal length, sepal width, petal width, etc. And just for demonstration purposes over here, we can just do like, it'll always be random. And then if we were to call the bagged features over here, let's just actually run this. We are going to have different features that are going to be chosen each time. So that's where the sampling part comes into play. And then with the formula, we'll be calling all of our features and related to the data set. So if there is a feature that was not called upon, then that data is going to be NA, and the tree is perfectly fine with that. So for classification predictions, we can have out of bag predictions over here, and we are going to be predicting with our given tree of our out of sample new data is equal to out of bag samples. And since this could be a classification problem, we have class as our type over here. So let's put this on a new line right here. So once we have our predictions, let's then calculate accuracy. Okay, accuracy from out of bag samples. And this is out of bag accuracy. And then we are going to call accuracy. This comes from the metrics library. And we're going to have our true values, which is the out of bag samples, and we're going to put that then to our target output. And then we're going to have our predictions is just out of bag predictions over here. Out of bag predictions. So we have a predicted values with our new data sets, and we are then can be calculating how well we've actually predicted based on our true values with our predicted values over here. We then want to return our trees to our model. So let's just do list of trees, go to tree, and we want to return our accuracy, out of bag accuracy. And let's call this out of bag accuracy. That's equal to this. So I think everything should run. Once we run our for loop, we want to then kill the cluster. So we can do this by just stopping the cluster over here and CL. And then let's return our RF models over here and see what happens. So let's run all of this. Oops. I think, you know what? I think it's for each over here. That is probably the reason why I am getting that error. Let's put this on a new line. Let's rerun everything. There we go. Okay, cool. And then we have our RF models. We have 100 of these models, RF models. So yep, we have 100 of these models, and we have a given accuracy for each of these models that have done its predictions. And then since we are doing a bagging algorithm, we are then going to just average everything up. So let's call this like a value, this val, to as apply of our RF models, and we are just going to be calling a function x, and it'll be just x of RF models of our RF models, which is at 2, which is going to be the out of bag accuracy that we have going on over here. And then we are going to take the mean of our values. So let's do unlist of our values, and we should have our overall values. So what's happening here is that the apply family is really neat. You just pass in your given lists, which RF models looks something like this. We have a bunch of lists that are within each of these matrices given here. We create a function, we pass in our entire data set into here, and then we'll be calling our second parameter, the out-of-bag accuracy, and it's going to be returning this into a different list. So let's run this, and the values look like this. So we have all of our out-of-bag accuracies, and then let's just take the mean of the unlisting of our values, and this is our bagging value. So this is our robust model. This contains all of our models, in this case 100 different models, and it just averages all of those predictions. You can even go into step further as to save all the tree weights, and once you save the tree weights, you can then aggregate all the weights and make a huge tree, which is the idea of the random forest. But if you like what you saw, make sure you leave a like and hit that subscribe button with the notifications on, and I hope to see you in the next video. Thank you for watching.